Aloha, welcome to the Newsvendor model lecture for supply chain management, Business 631. Today we're going to talk about the Newsvendor model, which is going to answer the question about how much should be ordered to match demand. It's our first microeconomic model. The Newsvendor model is a very simple but very interesting problem, has kind of an interesting history, but a profound kind of applications. And the idea is about too much and too little. So the idea is that if demand for something, say newspapers, is uncertain, we need to know how many newspapers we should print, and then of course put out to newspaper vending machines, etc., to make sure that we meet the demand. But there's a problem in that it costs, every newspaper costs something to produce. And we don't want to overproduce because then we'll have a bunch of leftover newspapers that we just have to either salvage, that means sell for less, or maybe throw away and get nothing back. But of course, if we produce too few newspapers, then the problem is that we will lose sales. So there's a cost to producing too much and a cost to produce too few. So this is going to be the general picture for looking at balancing the overage cost versus the underage cost for overproducing or underproducing papers based on demand. The whole key to that is is that the demand for the newspapers is uncertain. We don't know how many there are. Interesting little side thing is that this problem appears to date from 1888, where a famous mathematician named Edgeworth used it to determine how many cash reserves were needed to satisfy withdrawals from depositors. It's kind of an interesting that it was a supply chain problem for cash, not newspapers. So the Newsvendor model has actually quite a lot of applications. It's quite a general little thing. And it's really useful for doing things like making inventory decisions for like fashion, clothing based on seasonality, or production capacities for consumables and perishables, or things like the blood supply to manage to keep a no hospital based on uncertain demand for, based on accidents and things like that. Maybe number of employees to put on a project, or even number of cell phone minutes to contract for. So there's a lot of different things that you can use it for. It's quite a flexible model. So let's kind of set up the basic Newsvendor problem and think about how this works. So let's think about a newsvendor who buys paper for, say, 10 cents a piece at 5 in the morning. And they sell them throughout the day for 50 cents a piece. So the profit for this, of course, is going to be 50 minus 10, 40 cents per unit of newspaper. That means every newspaper we make 40 cents. And there's going to be a loss of 10 cents for every newspaper that we don't sell, because that's what it costs us to purchase it. Let's just say that the average daily demand is 100 units. How many newspapers should we order? Well, this is dependent on a couple of things. As with anything, we're going to have to make some simplifying assumptions. We're going to have to understand if this is the average daily demand. We have to understand what the demand looks like as in terms of uncertainty. So we're going to assume that the demand is normally distributed with a mean 100 and a standard deviation of 20. Now, whether or not the demand actually is normally distributed is really not as important as the relationship that it has with the problem itself. So people can argue about whether demand for newspapers is bell-shaped or not. But in some sense, it won't actually matter because the results will be more or less the same. But in this case, it's perfectly reasonable to think that the demand is normally distributed, because what we really want to do is just understand how the variability of the demand affects the number that we would order. So again, it's going to have to do with the relationship. So you can, if you need to change this assumption, it's not that difficult to extend the model to something different if you think that distribution isn't right. Normal distribution is a perfectly good, reasonable approximate for many different kinds of situations. And this one will be really easy to analyze. So remember that the Normal distribution means that it's bell-shaped. That means that the mean is right in the middle, and we expect equally that we'll have more than that demand or less than the average demand. So we have 100 newspapers that was the expected demand. Of course, we don't really think we're going to have exactly 100, but it's equally likely that we're going to have more than 100 or less than 100. But as we increase the potential demand, that becomes less and less likely. Also, if we decrease it, it becomes less and less likely. Most of the demand is going to cluster around the mean, and that's what we mean by normally distributed, that it just tends to be around the mean. We're going to have some terminology here that call it overage, means that we order too much and we have inventory left over at the end of the day. So that means we have newspapers left over that we didn't sell. An underage means we sold too little and we lost sales because we didn't have enough newspapers available to sell. So we made the loss here is not it's not like a physical loss, because it's not that we actually had money and lost it. It's the potential to earn money, and that's kind of what we call an opportunity cost. So these losses these are both considered losses. So this is really more of a tangible economic loss. I mean, literally, you just lose money because you sunk money into it. So we call it the sunk costs or the expenditures. And this one is an underage cost, which is not really that kind of loss. It's an opportunity loss. It was an opportunity to profit that we didn't make. But nonetheless, it's still a loss. So if we're given that demand is normally distributed, if we don't have any financial information at all, in other words, we don't know what the overage or underage costs or losses would be, we'd still probably order just the mean. In other words, an average amount, or in this case, our example of 100 newspapers. And that's because we don't really have any reason not to. In other words, the average of 100 newspapers, that's what we expect. We expect to sell 100 newspapers. On average, we sell. Now, of course, we're going to sell a little bit more, a little bit less. But if we don't know anything about how much it costs us to have too many or too few, in other words, an underage and overage, then our best bet is to just go with the average. Think about that for a second, but you'll understand. Now, let's just say that we do calculate what we expect the too much and too little, or the overage and underage costs would be. Now, we usually use the symbol CO, little o, to be the overage cost. Now, the overage cost is going to be calculated per unit. So if we're thinking about newspapers, it's going to be the overage cost per newspaper. It's very important that you understand that we're going to look at the per unit cost and not the overage cost over all the newspapers. Again, that sometimes we call what is known as the sunk cost, and it's a little tricky to think about, because what does it mean to talk about the overage per unit? It's the cost that we would incur, or the loss, but instead of the way that we get the loss is we think about how much it would cost us to order one more unit than what we would have ordered had we known the demand. In other words, if we sold, if we had 101 units and we only sold 100, so we had one more than what we needed. So it's the cost of having that one extra one that would cost us if we had known that we were only going to sell 100, which means that we might be able to recover some if we had known that demand was. So sometimes we look at other factors. So you have to be very careful about thinking about what goes into the overage cost per unit. It has to be that what is that cost of having one more if we knew what the demand was. So usually we can think about what the cost of, say, the newspaper is minus how much we'd get back for salvaging that newspaper. Well, if we assume that we don't get anything back for selling a newspaper when it's old, because who wants an old newspaper, then if the newspaper costs us 10 cents, we salvage nothing. Therefore, the overage cost per unit is 10 cents. Now, CU, the underage cost per unit, it's the same thing. Again, it's the cost of ordering one unit fewer than we would have ordered if we had known the demand. So in this case, maybe we what if we ordered 99 and we actually knew that we were going to sell 100? So what would be the cost of ordering? What was the cost for having that one less, even though we knew it was 100? It's a little tricky to think about, so you'll have to get used to that kind of thinking. So let's just say we had a lost sales, so we under-ordered. So we had 99 newspapers, and the CU, or the underage cost, would be how much profit we would have gotten had we had that 100th paper and we had the opportunity to sell it. So basically that would be, in this case for the newspaper, it would be the price of the newspaper that we would sell it for, which is 50 cents, minus how much we paid for the newspaper. Because remember, we still have to pay for that newspaper if we sold it. And so we would lose, we don't get to enjoy that if we had that. We only get to enjoy 40 cents. Often people forget this and they just look at the 50 cents. They don't realize that they wouldn't have gotten the 10 cents because they would have had to spend it to have that 100th unit, that 100th newspaper. Okay, so how much to order? And intuitively, we have to think about this intuitive, that if the underage cost is more than the overage cost. So let's say that we have a cost for not having enough is more. In other words, we stand to lose more if we don't have enough than for too much. Now again, we're going to assume the demand is normally distributed, which represents the variability or the uncertainty. So Q is going to be the amount that we'd like to order. And if the underage cost is more than the overage, then we should probably order more than the average that we expect to sell. In other words, you have to think about this. Because it costs us more to have too few, and we expect to sell the 100 newspapers, we're going to probably order actually a few more newspapers than 100 just to make sure that we have enough to sell, because it hurts us more not to have enough. So it's better to have too many, more than the mean, than less than the mean. How many more? Well, how can we figure that out? Well, knowing that the demand is normally distributed, this is actually pretty easy to figure out. How does the overage and how much the underage cost affect the quantity? So let's think about this. Let's derive this Newsvendor thing, the model itself. So marginal means that if given a certain condition, what would be our what would be the values for things. So let's just start that we order 0, and we consider now ordering 1 paper and 2 papers all the way up to Q papers. Let's let f of a, so this is going to be some function of a, be that the probability that demand is less than a. So in other words, this is going to say how likely is it that we'd sell this many or less, or a or less newspapers. So f of a, again, is the probability or how likely that we sell a or less newspapers. So the incremental cost of going to the qth unit, now, so we go up to the qth unit. We buy 0, 1, 2, 3, 1 unit at a time. Okay, so if the qth unit is not purchased, if that qth newspaper isn't, then we lose O. In other words, that's how much, because we had 1 too many. So if we don't get that qth one, we lose exactly that 1 unit. So the expected cost of the qth unit is going to be the probability of not selling that unit, like how likely that we don't sell that qth unit, times how much we lose, which is C0. In other words, f of q times C0. Remember, f of a is the probability demand is less than a, right? So, in other words, the qth unit is not demanded, so f of q would be the probability that we sold q or less. So let's take a look at this more formally. Let's look at the marginal, which is given a certain situation, how much we would stand to expect to lose or gain based on overage and underage. So let's just start with that we ordered 0 newspapers. We consider going to ordering 1 newspaper, 2 newspapers, all the way up to Q newspapers. Now, if we set that f of A is going to be the probability that demand is less than A. In other words, how likely is it that we sell less than A newspapers? The incremental cost of going up to the Qth unit, in other words, how much does it cost us to go to the Qth unit? And let's just say that we don't sell that Qth paper. Okay, so let's look if we have, what's the cost of going to the 100th paper from 99? Now, if the 100th paper, the Qth unit, is not demanded, we lose that unit cost, or C0. So the expected cost of the Qth unit is going to be the probability that we didn't sell that Qth unit, or the 100th unit, times how much it costs us, which is C0. In other words, f of Q times C0. Remember, f of A is the probability demand is less than A, so f of Q is the probability demand is less than Q. So if Q is 100, it would be the probability of selling less than 100 units, but not 100 units, times the cost of what we lose for having that 100th unit, because it's just one more. Now, the incremental benefit of going to the Qth unit means if we do get that Qth unit, if we do get the 100th unit, we gain the CU. In other words, that underage cost is what we would have expected to lose had we not had it available, but it was available, so we get it, right? So the expected benefit, again, is the probability of actually selling that Qth unit times that expected benefit, which is CU, or the probability of selling is just 1 minus not selling it, so 1 minus f of Q times CU. So the optimal order quantity, or this Q star that we're looking for, is going to be where the expected cost equals the expected benefit. In other words, if we go too far, if we order too many, if Q is too big, we're going to start to lose, right? But if we order too few, then we're not going to get the benefit from selling more that we have. So we look to see where they're exactly equal. So this is the expected loss of not selling, and this is the expected loss from, this is the expected loss from not selling, and this is the expected loss from having too many. So exactly where these things are equal is going to be the place we want to find what value of Q makes these two equal. Now, the interesting thing that you may not have seen before is that we're looking at a little equation here for which there is uncertainty. In other words, this is the probability that the demand is less than A. So we're kind of looking at where the probabilities times these fixed values actually balance out. If you solve this for Q star, you'll see, well, first solve for f of Q star. You'll see that we get this thing called the critical ratio. C, the underage, divided by the underage plus the overage. So this ratio here, we call the critical ratio, is going to be that point that is going to balance out the underage and the overage costs, so that the likelihood is going to be based on how likely it is we sell Q star. Now, we often call this probability that we sell that less than this, we call it the service level. In other words, it's the probability that demand can be met, or how likely it is that the demand can be met. So the service level, again, is the same thing as the probability that the demand is less than Q. Service level, probability demand less than Q, same thing. So if we know that the service level is supposed to be equal to the critical ratio, because that's the place where the underages and overages, the expected underage and the expected overage losses balance out per unit, then that is going to be the place that we're going to determine how many we should order. So the service level will be determined by how much it costs us to be over versus under. And it's kind of interesting to see how that works. So let's look at the newspaper problem again. And then again, we buy it for 10 cents at 5 a.m. We sell it throughout the day for 50 cents. And let's just say, so the underage cost is going to be 40 cents as we determined before. The overage cost is 10 cents per unit. So looking at the underage divided by the overage plus underage plus overage, we get a critical ratio of 0.8. Hence, the service level is going to be 80%. In other words, it's 80% likely that we're going to sell that many or some number of newspapers or less. That's going to be our service level that we can provide at the optimal underage and overage, okay, where the optimal is. So F of Q is the demand. Actually, this should be F of Q star. The probability that is less than Q star is equal to 0.8. So we want to choose it so that is less than Q. So how do we figure that out? So we have this weird problem that now we have that a probability is equal to 0.8. But this just brings us back to basic statistics now, because we could figure out what value Q, if we know the mean and the standard deviation, right, for a normal distribution, we can figure out what value would give us 80%, for which the probability is less than that, okay? So going back to business 621, not 630, business 621. So we go back and that's business 621, the basic statistics again. This Q star is going to be somewhere. Now we know that that's past the mean. How do we know it's past the mean? Well, if the service level is supposed to be if more than 50%, the mean is where the service level will be exactly 50%. So if the service level is supposed to be more than 50%, then the number of newspapers we need to order has to be greater than the mean. And similarly, if it was less than 50%, it would have to be less than the mean. Because remember, the area under this curve has to be 80%. So somehow, remember up to the mean, it's only 50%. So up past that, it's more than 50%. So the real question is, how many standard deviations away from the mean should we order so that the probability demand being less than the order quantity is 0.8? So it just brings us back to this basic problem again in statistics, is how many standard deviations from the mean will give us a probability of 0.8. And we can figure that out. Let me just set that up. We just said that, so F of Q star is the probability demand is less than Q star. That's the same thing as saying now this phi of Z means the standard normal distribution. So phi of Z, given the standard normal, well, the mean is 0, standard deviation 1, right, is where is the standard normal equal to 0.8? And what we can do is once we know this little z, this is going to be the number of standard deviations away, right? And then we can use that to figure out, given the actual mean and standard deviation of our demand, we can figure out what the actual Q is. So once we know how many standard deviations away to give us the critical ratio, in other words 0.8 for our problem, we can then convert that into the non-standard normal, whose mean is mu, standard deviation is sigma, by just using this simple formula to convert it back. In other words, the optimal quantity to order would be the mean of the demand plus the number of standard deviations that give us the critical ratio times the standard deviation of our demand. So you can see how this works. In other words, if there were no variability at all, remember, if there were no demand variability, sigma would be 0, right? We would just order mu. But noting that if z is positive, right, then we would order more than the mean. If z is negative, we'd order less. So the question really amounts to finding the standard normal of z equal to 0.8. And if you don't remember how to do that, there's a little reminder tutorial on how to do that. You can look it up in tables or use Excel. So going back to the solution for our original problem, knowing that the demand is normally distributed with the mean 100, standard deviation 20, all we have to do is figure out what z gives us 0.8. In other words, what standard normal value gives 0.8. We can use the standard normal tables, or you can just use Excel and look at the inverse normal. And we found the closest number on the standard normal table, let's just say, is 0.7995. Let's just take a look at those standard normal tables. I'll click on that. So listen, I put these in the back of the slides for convenient. You can see here's the standard normal table. Again, you could use Excel to do this if you wanted. So we say the closest value to 0.8 is 0.7995. That's a little too much. That's a little too little. So 0.7995. That gives us a z of 0.81234. So 0.84. So 0.84 is our z value, and now all we have to do is calculate the q from that. Again, we could have just used the normal inverse function Excel if we wanted to. How do we calculate q? Just plug in the mean plus our z value times the standard deviation, 117 newspapers. So again, if we want to have a service level of 0.8, which is going to balance the underage and overage costs, because the underage is more than the overage, we would expect that we want to keep more newspapers. How many more? 17 more than the average. Because we said the mean was 100, so we would expect to keep 100 if we didn't know about the underage and overage. The way we look at this is that remember that mu is going to be how many newspapers we'd keep if we didn't know about underage and overage. But since that demand is uncertain, the z is going to be what we call the safety factor or whatever it is. It's basically going to be positive if we need to keep more newspapers, negative if we need to keep fewer. This is the point that balances the underage and overage costs exactly. And it's going to be proportional to how variable it is, which is represented by the standard deviation. So notice that the more variability we have, the more uncertain the demand is, the more newspapers we'd have to keep and buffer. Okay? Or unless this was negative, then we'd have to keep less. So, who killed the newspaper? I don't know. It's the radio stars. Let's think about this, who killed the newspaper, more in a different light. Let's say that advertisers are moving to online media, and that's what killed our newspapers. And the cost of newspapers have gone up to try to cover the loss of advertisers. So the newspaper vendor must buy newspapers at 25 cents instead of 10 cents. So they're more expensive now. And now fewer people are buying newspapers. So the demand profile says that the newspaper sells at 40 cents instead of 50 cents. So in other words, if I want to expect to sell 100 papers, I can't sell it for 50 cents. I have to drop my price to 40 cents. Now what's the order quantity we should order? Now it's going to be a little bit different. So the underage cost, again, is we still pay 40 cents. We sell the newspaper for 40 cents, right? But now we pay 25 cents. So we actually have an underage cost of 15 cents per unit. So if we don't sell, for every paper that we could have sold but we didn't have, we had an opportunity loss of 15 cents or a potential profit of 15 cents. The overage cost is now 25 cents per unit because, again, we have to pay for that newspaper and we don't get anything back if we have too many. So here, the overage is more than the underage. So the critical ratio now, again, take the underage divided by the underage plus the overage, is 0.375. So notice that the critical ratio is less. In particular, it's less than 0.5, which is really interesting. So our service level is going to be less than 50%. If you look up what's the standard normal value that gives 37.5%, you're going to get a z of minus 0.32. Again, we're going to know it's minus because it's going to be less than the mean. It's going to be less than the mean because this is less than 0.5. So plugging this into our formula, again, we expect to sell 100 units plus the negative z value, 0.32, times our standard deviation 20. Now it says that we should only keep 94. In other words, don't order more newspapers, hold less, and allow yourself to sell out because it costs us, it hurts us more to have expensive newspapers than it is to lose sales. In other words, the optimal order quantity, in this case, based on the economics, means do not order the mean. Don't order the mean. Order less than the mean. We don't actually want supply to equal demand. Weirdly enough, because of the economics of this, it balances this. Just like before, we wouldn't want to order the mean because we expect to gain more if we don't have sales, if we lose out on sales, if we don't lose out on sales. So what does this mean for the normal distribution? Again, pictorially, you can look at, once again, our critical value is less than 0.5, which is where the mean is. So the critical value of the mean is always 0.5. And so we want to know what area, so what value of Q star will give us an area of 0.375 or 37.5%. Looking it up, you see that this value of z equal minus 0.32. In other words, negative 0.32 standard deviations from the mean is what's going to give it. So you actually can think about this by just looking at the ratio of underage and underage. So the critical ratio is the ratio of the underage divided by the underage plus the overage. But you could simply just look at when the overage and what is the ratio of the overage to underage? So when the underage and the overage are exactly the same, of course we don't expect to lose any more from loss of sales versus having too many, so we would just order the mean. That's obvious. But let's think of the situation where the overage divided by the underage is, say, 10%. So in other words, that the underage is much more than the overage. So in this case, you can figure it out that the critical ratio might be 0.91, and this case is going to be 91% of the area, so we'd want to order more than the average, considerably more, because our underage will cost us more than the overage. Similarly, again, what if we get a little closer? What if it's not that dramatic? What if the underage and the overage and underage is 2/3? So just say they're pretty close to each other. Then you start to see that we're only about 60% of the area here, and we're getting closer to what the mean would be. Now, what happens when the overage and the underage is exactly the same? Of course, we'd order the mean. And that, again, because it doesn't cost us any more to have too many as also having too few. And now, if the overage is larger than the underage, say that the ratio is 2, then you can see that we're going to want to hold less because it hurts us to have more than less. So the intuition seems to hold through to this model. You can reinforce this by thinking about a lot of people have trouble understanding because of the normal distribution, the ratios aren't exactly linear. In other words, it's not exactly proportional. It's going to be proportional to the variability here, which is the standard deviation. And the z, of course, is going to be relative to the normal distribution. So if you want to take a look at what, as the overage underage ratio, say, increases, what happens to the value of z? You can see that as our overage and underage, so here's where it's exactly 1. Notice that the value is exactly 0 for z. But you see what happens is that as the overage and the underage ratio increases, you see it sharply decreases, right? And then it's more slowly, then it still sharply decreases more, but less and less as we go further on. Again, this is an artifact of the normal distribution. So how do we solve Newsvendor kind of problems? Well, first of all, so recognize you have a Newsvendor problem. You have a Newsvendor problem when you have a single optimal decision before the uncertainty is resolved. So what do we mean? We need to figure out like some sort of what's the best thing, how much of this, or what's the optimal that, minimum that, before we know how many things are actually sold. So in this case, so that's what we mean by uncertainty is resolved. We need to make the decision before we know the actual demand. So the first step, of course, is to figure out what the overage and underage costs per unit are. Remember, they have to be per unit, not overall. It's very common to make the mistake of looking at underage and overages overall or fixed costs, but it has to be per unit. Calculate the critical ratio. Find the Z value for that critical ratio by looking at the inverse standard normal. And then calculate the profit maximizing order quantity Q star by just plugging it in to converting the standard normal back into the normal with mean U and standard deviation sigma. So when you're doing a Newsvendor problem, keep in mind that your assumptions that demand is normally distributed and that the underage and overage are the only financial factors. But if you have other financial factors that come into play, then you don't have a Newsvendor problem. Things like fixed prices, costs, and lead times, and things like that do affect our situation, but they are not relevant to a Newsvendor problem. So let's take another example. Let's look at greeting cards. Let's say we have a Thanksgiving cards at Walmart that we're trying to sell, and we want to know how many to put on the shelf. So let's assume that the demand for a particular card is normally distributed with a mean of 500, standard deviation 50. So that means 500 cards we expect to sell with a variability of 50. Assume that Walmart sells the cards at $4.50 and buys them for $1, so they get a profit of $3.50. And assume that any sold cars for the season can be sold back to the manufacturer at 50 cents, so we get some sort of salvage. How do we evaluate the overage and underage per unit? Well, pretty easy. Okay, our overage is going to be the dollar that we pay for, because that's our sunk costs, minus the 50 cents that we get back from salvage. So the overage cost per unit the cost of having one too many would be 50 cents. The underage would be how much we expect to sell it for $4.50 minus how much we paid for it. So the opportunity loss would be $3.50. So we would lose $3, the opportunity to gain $3.50 if we didn't have a card to sell. So looking at the critical ratio, the underage divided by the underage plus the overage gives us 0.875. Okay, so service level of 87.5. This is the probability that we sell out. Okay, sell a certain number of cards or less is going to be 87.5 at the optimal value. So the optimal order quantity is just looking at the standard normal. So to look at the Z value for 0.875, you invert this, gives a Z value of 1.15. Again, we expect this Z value to be greater than 0.5. Why? Because the service level is greater than 0.5. So in other words, we'd expect this to be positive. We expect the Z to be positive because our service level is greater than 50%. So the profit maximizing order quantity would simply be the 500 that we expect to sell plus the safety loading 1.15 times standard deviation 50, or order 558 cards. So in other words, keep more than we expect to sell. Okay, so the insights on this is that if your underage is greater than the overage, then think about your service level being greater than 50%. If it's less than the overage, then it's going to be less than 50%, which implies that the safety factor, Z, is going to be, or the loading factor, is going to be either greater than 0 or less than 0. It means keep more or keep fewer than the average amount, expected demand, sorry. And the optimal order quantity is going to be greater than the mean demand or less than demand. I already said that. And notice that as the amount that you want to order will increase or decrease depending in relation to how variable the demand is. So as the demand increases, then the amount that you want to keep more or less than the optimal than the mean would increase. So there's always these questions about the company's targeted service levels in real business. In other words, if you didn't know any financial information, if you didn't know about underage and overage, in other words, not all companies tend to think about what's my profit maximizing amount. They often think about, well, I want to make sure I have product on the shelf, because if I don't have product on the shelf and people come to buy it, they're going to be disappointed. And so they think about things like, what is a 98% service level? You tell you about underage and overage cost. In other words, if I want to maintain 98% of the time that I have that I meet the demand or don't sell out, what does that tell you about our underage and overage costs? Well, you can think about that pretty easily. In other words, you can see that if I want to keep a 98% service level, under many situations, I'm probably going to be eating it in overage costs. So as uncertainty increases, you would expect to stock more or less for different things. So let's think about these kinds of questions. Now, as uncertainty increases, what would you expect to stock more or less for candy for Halloween in your store? Think about that. How about rare medications in a small independent pharmacy? What about spare parts for an F-16 fighter jet or staff in a small cafe? So these are some questions you can think about. We'll go over these in class further, but let's just take an example of this. Now, I didn't give you any financial information about underage and overage costs, but candy for Halloween in your store. Well, let's say that Halloween is the time we sell most of our candy, and so if we don't have candy on the shelves, we have the lose the opportunity for getting that candy, for selling that candy to our customers. So they're probably going to go to another store that does have the candy. So we miss out on that customer too. So we have kind of a loss of confidence by our customers. So one would think that perhaps the underage cost for not having candy on our shelf is more than our overage cost having candy on our shelf. And you can see this every time you go to most stores. They way overstock their Halloween candy. Notice that after Halloween's over, you can always find great deals on Halloween candy. 50% off, 90% off. They're getting their salvage value out of it. But obviously they've anticipated that the overage cost is much less than the underage cost. So in this case, as uncertainty increases, we're probably going to want to put more candy on our shelves. You can think about some of these other situations. Again, we can kind of solve some problems just intuitively without even looking at any numbers. Let's solve a particular one on our own here by looking at the Session 1 Newsvendor in-class problem 2A. So here it is. So this is some class exercises. If you're unfamiliar with the normal distribution and finding probabilities and values, here's some practice ones on question 1A through D. But we're going to go to 2A here. And in this case, we have a small fruit stand on campus selling fresh mango from the tree in our backyard. Now, we can sell mango for $4 each. And usually every weekday from about 9 to 4, we can sell 50 mangoes on average, but it varies and is normally distributed with a standard deviation of 10 mangoes. So if around 4 o'clock when I want to take off, I have mangoes unsold, I'll cut the price to $2, half price. And knowing that we can sell the leftovers, sure, because we don't want to bring any unsold mango home and get yelled at by who's ever there expecting us to sell the mangoes. So for each mango we bring from home, we promise to bring back $3. Now that's how much we pay for the mango. We want to maximize our profit. So how many mangoes should we bring to our stand? So in other words, this is going to be a Newsvendor type problem because we need to figure out how many we should order before we know what the demand is, or how many should we have on hand before we know how many are going to be bought. So how do we figure this out? Well, let's do it. Let's do it first by just grinding it out. So the first thing you want to do when you have these kinds of problems is you want to write out all your information, and that way you keep it straight because it's very easy to make a mistake. So the first thing we're going to want to do is let's write down our demand information. So demand for mango, right, is, let's insert symbol. We're going to use mu. We're going to need this too. Mu equals, so mu is the mean number of mango, and it's on average 50. It's right there. And the standard deviation, which we'll call sigma, is 10 mango. So 50 mango and standard deviation of 10 mango. And our price, okay, is, well, let's say sell is, well, let's say price. Price is $4 a mango. And our cost, that's how much we have to give our wife or husband or whatever, is $3 a mango. And if we, for every mango that we don't sell, right, we cut it 50%. So we get $2 for, instead of $4. So we'll call this salvage. $2 a mango. Okay, so how do we figure out the underage cost? Well, the underage cost is going to be our what we would have gotten if we were able to sell a mango that we didn't have. So that's just going to be the amount of profit. So that's going to be the price minus the cost, right? In other words, $4 minus $3 equals $1. And the overage cost is going to be, well, this is if we had one mango left over, then how much did it cost us minus how much we can get back from selling it at half price. So it's cost minus salvage, which is going to be equal to $3 minus $2, once again, $1. Okay, so our critical ratio is going to be CU, the underage, divided by the underage plus the overage, which is 1 divided by 1 plus 1, right? Everything's 1, very easy. It's going to be equal to 0.5. Okay, that's easy. That means we already know what this means. So in other words, if we have a critical ratio of 0.5, that's right there in the middle, right? 50% service level means that our Z, our loading factor, has to be 0. I don't even have to look that up. It's going to be right there in the middle because, again, 50% of the area under the curve is exactly, for a normal distribution, is where Z is. If you wanted to, you could do an inverse normal or look this up, but it's not necessary. So Q star is going to be equal to, right, mu 50, right, mangoes, plus Z 0.5, 0 times 10 mango, okay, which is just going to be equal to 50. So that's how many we should have. But this is obvious. This is grinding it all out. But once we know that the underage and the overage are exactly the same, we already know that we should just keep the average demand because we know that the critical ratio is going to be 0.5. So we didn't actually need to grind that out, did we? Just keeping things straight is all you need to do. Now, as I pointed out, we don't really need to have the actual overage and underage costs for many situations. Sometimes it's actually difficult to get the per unit underage and the per unit overage costs. It's sometimes not easy to get that data, or it's complicated. But really all we need to know is the ratio of the underage to overage, which sometimes is a lot easier. So in other words, if we look at the critical ratio, just do some algebra, you can rearrange this, and you can see that the critical ratio is equal to 1 over 1 plus the overage divided by the underage. And again, we looked at that before, remember? So in other words, if we just know what this ratio is, or you can see if it's bigger than 1 or less than 1, we can kind of get an idea of what this is. It's often difficult to get good numbers for some of these things because sometimes when we think about the loss of goodwill, for example, like a customer came to the store and wasn't able to purchase something and they get disappointed and they go to another store instead of us, it's very hard to kind of put a dollar figure on that. Like, what's the loss of a customer? There are other kinds of news vendor type problems, but it's not exactly the news vendor model, but sort of variations of it. So it happens when so you know a news vendor problem when you're trying to optimize the profit, like you're trying to optimize the losses. You want to minimize the losses or maximize the profits. But sometimes we don't want to make those particular decisions. Sometimes we just want to know, like, what's the order quantity be for a given service level. And I say we just don't want to stock out. We just want to have stuff on the shelf, and we want to know how many we have to keep. It's actually a simpler version. It's not even the news vendor problem. It's actually simpler. So what we'd want to do is basically, given a certain service level, we find out what the loading factor would be, and then if we know what the demand is, if it's normally distributed with mean mu and standard deviation sigma, we just plug that in. That's pretty easy. Sometimes we want to know that what the service level is given a quantity, like what service level we'd be able to provide if we had this many units. In this case, we don't need, just like over here, we don't actually need to evaluate overage and underage. All we have to do is just calculate what the z-value is. So how we can calculate the z-value? Well, we know that we have this order quantity Q, and we know what the mean demand is and the standard deviation is, so just solve for z. And now, using that z, just figure out what that standard normal value is, and that will tell us the service level. So these actually are easier variations of the news vendor problem. Let's take an example here. What is the service level if we have 115 newspapers? Once again, we have 115 newspapers, and we know that there's demand of 100 and standard deviation of 20 newspapers, so the z-value would be 0.75. Looking at the standard normal table, what is the standard normal of 0.75? Going to give us 77.34%. Again, you can go look that up at the table or use Excel. Let's try solving this problem for our mango stand. So what if our spouse forces us to bring 60 mangoes? Well, if our spouse forces us to bring 60 mangoes, what's the likelihood that we're going to have to cut the price and sell leftovers after 4 p.m.? Well, that means what's the likelihood that we stock out or that we sell less than 60 mangoes? We bring 60 mangoes, we want to know the probability. The same thing as asking what's the service level. Okay, so we can figure that out. The first thing we do is know that the value z, right, our safety factor, is going to be equal to it's going to be equal to 60. That's how much our spouse forced us to bring, minus the average demand, which is 50, divided by the standard deviation, which was 10. So that's going to give us a value of 1. 10 divided by 10. And so we want to look at the probability that the demand is less than 60, right? Well, that's going to be same thing as the probability that the z is less than 1. Again, this is basic statistics again. So remember, demand is where we have, D is the demand for mangoes with mean 50, standard deviation 10. Z is just the standard normal, where the mean is 1 and the standard deviation, the mean is 0, standard deviation is 1. And so that's this z here. So with the probability that z is less than 1, looking that up on the table, we're going to get 84.5%. 98.13%. So we can have a service level of about 84%. 84% of the time, we're not going to have to cut the price. The probability that we will have to cut the price would be 1 minus this. Because this is that we sell less than that. Oh, sorry, have that reverse. This is the probability that we sell less than 60. So 84% of the time we're going to sell less than 60. So that's how often we're going to have to cut the price. 1 minus it would be how likely that we wouldn't have to cut the price. Okay, so moving along. Let's look at that other Newsvendor type problem. What if we had we want to have newspapers 98.5% of the time. So we want to have a high service level. We always want to make sure we have newspapers. So that means that the service level is already going to be set at 0.985. And so we just look up in the standard normal table what Z corresponds to 0.985. The Z value for 0.985 is going to be 2.17. Plug that into our mean plus that Z times standard deviation. We'd want to have 143 newspapers if we wanted to maintain a service level of 98.5. Again, this is not the financially optimal quantity. Remember, this is to maintain a service level of 98.5%. In other words, that we don't sell out that amount of time. So let's try another problem again. So let's just say that we plan to go to the gym after 4 p.m. and you want to reduce the chance that we have to stay after 4 p.m. to sell all our mangoes. So we want to have at least 90% chance that there will be no left over to sell after 4 p.m. So how many mangoes should we plan to bring? Okay, so the question really is we want the probability that we're greater than or equal to. Let's put the right symbol in here. Probability that the number of mangoes is set by a certain amount, right? We don't know what that is equal to 0.9. So we're just back to our standard, statistics kind of problem. How do we figure that out? Well, what we need to do is figure out that this is the same thing. This is the same thing. If you want to look at it, you can just look it up in a standard normal table once again. But we should start out by saying, if we're going to look it up in a table, we'd have to convert this to a Z value. So we'd look at what's the probability that Z is less than something is equal to 0.9, right? So in other words, if we can find this Z value, right, then we can find the D value by just multiplying by the mean and the standard deviation. So looking this up in a standard normal table, we see that that if we get made a mistake here. This should be that, and we should look at this should be made a little mistake. I hope you caught that. Is the same thing that Z is less than something is equal to 0.1. In other words, if we want to see whether something is greater than that is 0.9, then we can see that something is less than this is 10%. Okay, so figuring that out at the standard table gives a Z equals minus 0.128. Now we know it's going to be negative because, again, this probability is less than 0.5. This one's greater than 0.5, but remember this is the greater than that. So we're looking at the left hand, looking at things less than. So greater than would be less than here, minus 1.28. Again, if you forget how to do this, there's a little tutorial that reminds you of these things. And we can always just use Excel to calculate all this stuff. So this is the same thing as now saying, okay, that's going to be equal to some value, this Q, the one that we want here, minus 50 divided by 10. In other words, this is remember, this z value is going to be equal to the value that we would order to make sure we have a 90% chance of being sold out, minus the standard deviation divided by minus the mean divided by the standard deviation. Okay, so once again, solving for the question mark would be 50 minus 10 times 1.28. And so that gives us about 37.2. Now you can't have 0.2 mangoes. So 37 mangoes. Get the closest one. So if we negotiate to bring only 37 mangoes, then we're going to be at least 90% sure that we sell out and we can go to the gym. Okay, so that's it. I hope that you've found that this was interesting. And the takeaways here is that managing demand uncertainty is that sometimes it's optimal not to meet the expected demand based on what the average demand would be, but to trade off the cost for the overage and the underage to help us balance our losses so that based on what we would expect to gain or lose by having too few or too many.